Today I would like to present the results of my research paper that was recently published. So the paper was done in collaboration with my PhD supervisor, Professor Maciej Zięba. And the title of today's talk and of the paper is the Treeflow, going beyond tree-based parametric probabilistic regression. So the topic is a bit different than on the agenda, but it's exactly the same. So let's begin. Before we go into the details of the method, I would like to start with the short recap and discuss the difference between deterministic versus probabilistic regression, because maybe not all of you are familiar with this differentiation. So we'll start with the use case of future state prediction. So let's consider the case that car is entering a roundabout. And what we want to predict is in which direction the car will go. So in the deterministic regression approach, there's like exactly one position that the model will predict. So we can observe that on this pink rectangle that our model is predicting. So it is predicting that the car go into the left. However, it does not reflect like the full story of what is happening on the situation, because this model is not considering the possibility of going right or going to straight. So here we've got the probabilistic regression that is not returning the point prediction, rather the whole probabilistic distribution that is marked by the heat map. So we can observe that it predicts that, okay, probably it can go on the left side, but also it can go straight. So this is like the very brief recap of that. So if I were to describe what the Treeflow, the method that we will be discussing today is, so I would say this is like the probabilistic regression method for tabular data with a flexible distribution. So here are like two examples of that. On the left side, we've got the estimated probability distribution for the observation from the univariate regression problem. So we can observe that the Treeflow that is marked in blue can find in the distribution B modality, and comparing to the cat boost, it returns like the multi-modal distribution, and cat boost is finding only can model it only by Gaussian. And when we go to the multivariate setup, so we have more dimension in the target distribution, it can also find multimodalities, and we see that this distribution is quite complex. So let's go into the full story that I want to talk to you today. So we'll start with the three facts regarding in general, the tabular data and the regression problems. So we start with the classical methods. So for the standard deterministic regression, we know that tree-based ensembles excel in such tasks. So for example, in the classification regression problems, especially with numerical and categorical data. So I'm almost 100% sure that most of you are familiar with this method on the slide. So we've got the random forest, cat boost, XGBoost, and LightGBM. So I won't go into the details of that method. So recently, there was some extensions of that method to the probabilistic setup. So for example, the NGBoost, CatBoost, and PGBM, and they were able to model the target variable using probabilistic distribution, and usually it was a Gaussian distribution or some distribution that were parametric. So they were modeled by probability functions that have some parameters that we can estimate. So I will briefly go through these three methods. So the first one is the NGBoost. So it's like a tree-based ensemble that is estimating the parameters of the selected parametric distributions. And it's optimizing some kind of the scoring rule. So for example, negative log likelihood or continuously ranked probability score. The next one is the cat boost that was extended to the probabilistic setup, and it was able to model only Gaussian distribution. But the difference between the NGBoost and cat boost is that the cat boost is modeling both parameters simultaneously. The last one is the PGBM that treats the leaf weights that are in the trees as random variables. However, it limits this method to only distribution that can be parameterized by scale and location. And however, this methods works quite well in the probabilistic setup. There are obviously some kind of the limitations. So the first one is that these methods struggle to handle multimodal distributions. And the second fact is that they do not support high-dimensional probabilistic predictions. So the predictions where the target variables have more than one dimension. So in fact, in terms of the multimodal distributions, like any of the method can really support that. And in terms of the high-dimensional probabilistic predictions, it's like the only method that can work in such setup is the NGBoost. However, the scalability of this method is it's not so good because we are just estimating all parameters, for example, of the Gaussian covariance matrix. And there's obviously workaround for that, so we can model each dimension of the target variable like separately. So we've got this kind of the independence approach, so we can use any kind of the model here. However, as we'll see in the later part of the presentation, it not yields the best results, obviously depending on the data set and the setup. So here comes the Treeflow, the method that we developed, and I would like to go through the details of that method. So we'll start with the main characteristics of the method. So short summary, what this method is about. So first of all, as I said previously, it's a regression model for tabular data. It can handle both numerical and categorical data. It can work both for univariate and multivariate targets, so both 1D and more than 1D target variables. It can model both non-Gaussian and non-parametric distributions. And what is important, the method can return both probabilistic scores and predictions and also deterministic predictions. So we can also go back to this point prediction setup. So let's briefly discuss the architecture of the method. So method is construct using three components. The first one is tree-based feature extractor, the second one is shallow feature extractor, and at the end we've got the conditional continuous normalizing flow. So this first part extracts the vector of binary features from the structure of tree-based ensemble model. And in a moment I will go into the details of the training, so I will talk a bit more about this one. The second part is the shallow feature extractor. This is like the shallow neural networks of two layers MLP that maps this high-dimensional vector from this tree ensemble to the lower dimensionality feature space. And at the end, we've got the conditional continuous normalizing flow that takes this vector of conditionings and models the complex probability distribution. So what is important is this component is crucial for this modeling flexibility of the distributions. And I would like to shortly discuss this normalizing flow because it's not maybe the most famous method. However, it's the main component of that approach. So if I were to discuss this method in like few sentences, so it's like we've got the series of transformations. So we've got the F, like the series of transformation, and what's important about this transformation is that they are differentiable and also invertible. And what we are doing is that we are taking the very simple probabilistic distribution that we can calculate log probability. So usually from the practical application, it's usually a standard Gaussian method. And yeah, we usually call that base distribution. And we want to transfer that distribution to the very complex distribution by this transformation and obtain this complex one. So it's in our case is the target distribution. So in terms of the training, so how the method is trained. So we've got the data and we've got our features. Oh, so maybe I'll start that we've got two stages of the training. So at the beginning, we've got the data and our features. We are training, in our case, the CAD-boost using the NLL criterion or multi-RMSE for the multi-dimensional case. And we are using CAD-boost mostly because if out-of-the-box support of categorical variables, because we want to support both numerical and categorical variables. After that, we extract the representation. So we are just taking the encoding of in which leaf the sample just landed. We also add the targets. And we are using in the second stage and we are training in the second stage the shallow feature extractor so this MLP, and conditional continuous normalizing flow. So we've got the representation here. Here we've got the target, the targets, and we are training this part of the network, and also we are just doing like the backward pass, let's say, of the distribution from the complex one to the simple Gaussian. So when the method is trained, what is important from perspective of our methods is the sampling from that method. So how will we do that? So we've got the data, so we've got the features, and we are creating this conditioning vector. So we are just putting that features through the tree-based feature extractor. We are extracting the binary vector. We are just putting that through the MLP network, and we've got this conditioning vector. And from the perspective of the normalizing flow, we are sampling the sample from the base distribution, so from the Gaussian. And we just using the forward pass of the normalizing flow to just convert this simple distribution using this conditioning factor to the target distribution, and we've got the sample. So the sample is especially important when we want to make the point prediction, because we are extracting the modes of this distribution to just predict the specific point. Okay, so that was the part of the method. So let's briefly discuss the experiments. So probably the first question that we might ask, so because I multiple times mentioned that, okay, so we are just focusing on the modeling of the complex distribution. However, what's the difference and why is that important? So in that case, we've got the estimated probability density function for two methods. So for the cat boost in yellow and for the Treeflow in blue. And we can observe that for the true value of that particular observation, the probability density function value for that value is very similar. So we can observe that here. However, the properties of this distribution is quite different. So starting from the cat boost, we see this is the Gaussian distribution, and we see that, for example, the negative values are quite likely, like looking for that function. However, we can see that first of all, the Treeflow got the quite heavy tail distribution, and it figure out that the negative values are like highly unlikely. And it's especially like important from that perspective because the data set was the wine reviews. So it's rather sensible to expect that the values won't be a negative, and we see that our model figure it out. However, you might ask, okay, so maybe the model is wrong. I mean, so maybe it's just modeling that distribution as some heavy tail distribution. However, it might be like not the true target distribution, underlying true distribution. And for the real cases, we don't know that. So we constructed the toy example where we wanted to check that. So we generated the very simple data set. We've got two variables, x1 and x2. And for different combination of that features, we sampled the values from simple distributions, so from the normal distribution, from exponential distribution, mixture of Gaussians and gamma, and we can see results here. So in the yellow again, it's a cat boost, so it's modeling everything as the Gaussian distribution because it's the assumption of that method. And for the Treeflow, we can see that it's very similar, the distributions to the underlying one. So we can observe that, okay, so it's finding this true target distribution that is underlying in the data set. So let's move forward to the part of the more broad experiments for the univariate probabilistic regression. So we can observe that the method is finding very complex distribution. So we seen this example on the previous slide. So we found the multi-modal distribution. So we've got two modes. However, there might be some more complex distribution. So for example, multi-modal, where also we have the heavy tail distribution. So it seems quite complex. But on the other hand, if the underlying distribution seems to be Gaussian, the method also finds this Gaussian distribution. In terms of the quantitative results, I just feel free to come to the poster session to see the results. Here I've got the tables. However, we've got one table here and some explanation for the multivariate probabilistic regression. So I started discussing at the beginning of the presentation, we can have different approaches to modeling the multivariate distribution. So we've got the independent approach. So we are just modeling each target dimension by separate models. So this is like this independent part. And we can see that, okay, so this is like the model did not find any correlation because it cannot. It seems that, okay, so this is like very simple distribution. When we go back, when we go to the NGBoost approach, when we are modeling like the full covariance matrix of the Gaussian distribution, we see that, okay, in this data set, the model found some correlation. And at the end, we've got the Treeflow. So it found not only the correlation here, but also it found the multimodality. So this is like one modality, the second one, and maybe probably the third one here. And what is important, we see that the result, at least for part of the data set, we see that it significantly improved the results. So we've got the, for example, Parkinson data set that we see the significant reduction of the NLL metric here, and also for other data sets. There are some data sets that the changes are not so different. So like our hypothesis is that probably here the underlying distribution is the Gaussian distribution. So you cannot model it in more complex way because it like goes into like the not very something specific, and we cannot find the better distribution if the underlying distribution is Gaussian simply. So that was all in terms of the whole presentation. So I would like to make a short summary of that. So first of all, for the first time, we've seen the usage of the tree-based models to flexibly model the probabilistic regression. We provided a novel approach for combining tree-based models with the conditional normalizing flow using this forest representation, binary forest representation. And we also obtained SOTA results for both probabilistic and deterministic predictions on some of the data set where we've seen that the distribution is more complex than Gaussian. So again, I just warm welcome to join to the poster session, also read the paper. And that's all from my side. Thank you very much for your attention. And if there are any questions, just feel free to ask.